Hello, we are going to present our final project that is the simulation of an aortic valve implant. The table of contents include the introduction, background, the objectives that are the general and specific objectives, the methodology that are the SolidWorks geometry, simulation and analysis, the results and discussion including pressure and shear stress, and finally conclusions and future work.
Well, let us begin. Most of us are aware of the dangers of cardiovascular disease and familiar with at least a few of its varieties, like coronary artery disease, high blood pressure, and heart attack, among others. According to the World Health Organization, heart disease is the main cause of death in the world, and the statistics show that it causes about 30% of the death cases globally, so it can be considered the number one leading cause of death. And according to the American Heart Association, about 60 million Americans currently suffer from some form of cardiovascular condition. Also, according to Dangas et al. In 2016, valvular heart disease, here called VHD, is a common cardiovascular pathology that affects around 100 million persons a year worldwide. Next. Well, in valvular heart diseases, deterioration of native heart valves is difficult to revert, leaving valve replacement as the only option. 43% of all the valvular heart diseases are of the aortic valve, and one of the primary management strategies to solve it is surgical replacement. They are mainly replaced with bioprosthetic heart valves, which generate flow patterns that mimic those of the normal human aortic valve, and are constructed from fixed porcine heart valves or bovine and porcine pericardial tissues.
Now talking about the background, in the work of J. Lee in 2020, a fluid structure interaction model of a bioprosthetic heart valve was designed. This study describes the development of a dynamic computer model of a bioprosthetic valve in the aortic section, using an experimental pulse duplicator platform. Using this study as a reference, it was decided to use their valve geometry as the base for our simulations. Also, in the work of Adi A. Basri et al. At 2014, a 3D geometry of a patient-specific aortic valve and aorta was utilized to carry out the computational fluid dynamic simulation of the effect of different valve opening angles on the hemodynamic properties. In this study, the wall shear stress developed and the pressure on the aorta and tricuspid valve were analyzed. This study was used as a reference to know what other hemodynamic properties can be analyzed with our geometric model. Finally, to consider blood as a neutronar fluid, despite blood shows all signs of non-neutronar fluid, we use the study of Tweed-Mute because according to him, the aorta high shear rates are present with a blood viscosity of approximately 3.5 cp for a 45% of hematocrit, and hence the blood can be considered as a neutronar fluid in this part. Next slide, please.
So we had a general objective for this project, which was to perform a static simulation of a porcine aortic valve in the systolic phase, and as specific objectives we had that we needed to evaluate a design previously implemented to determine if our model was reliable, and we also had to simulate the pressure and the shear stress generated in the artificial aortic valve in a static model during the systolic phase.
The methodology that we apply to create our valve. First, we have to talk about the geometry. Here we have a model of the Hankook 2 valve that was implemented since 30 years ago by Medtronic, which is the industry that created, and we have different dimensions that we follow in order to design our bioprosthetic valve. We are going to analyze it in the aortic pathway. The different measures that we have, for example, in section C, the final distance is going to be 27 millimeters. Next. And how we're going to create this, we're going to use the SolidWorks flow simulations, computational fluidic dynamics software, and we're going to use static analysis. the different parameters that we found in different literature reviews. For example, the one created with the Wenmetu and Praki in 2018 was utilizing flow viscosity of 3.5 centipares and density of 1060 kilograms per meter to the third power, a flow of 15 liters per minute. This is because the program does not allow us to use less flow, because in normal conditions of the body, we have 5 liters per minute, even though that in exercise it is possible to be up to 20. So it's a good range to use 15, but this is given by the program itself. And the environmental pressure that we used was systolic pressure plus atmospheric pressure. Next, please. Here we have a slide also from Medtronic of the valve that we are going to expect to analyze and create. In our model, we're gonna use only section B, which is an open valve. And why did we select this model? Because it has 97.8% of variability in the aortic design. Next, please. Here we present our first results of what we created using the SolidWorks software. It's a render of our bioprosthetic design using the previous measurements that we show. And here we can see in section A a superior view, inferior view, anterior view, and perspective view. Here is a little design at the video, so we can see how it actually looks from different angles. And that's it for the geometry part. Now we're going to talk about the analysis of the flow.
Well, as mentioned before, we are going to analyze wall shear stress, pressure, but also we can see the pattern of the flow. As we can see, after the valve, we can see that the flow tends to have a high velocity after going from the valve, and then it can normalize. It's a little turbulent there, but it's fine, since we saw that in our model, our maximum velocity, which corresponds to the red color of the simulation, is around 1.4 meters per second. And according to a paper that we see in the right image, the velocity in normal parent or healthy for systole is around 1.2. That corresponds to the green color of the first image of the second image that is to the right. And then we also see that when there is a severely calcified model, that is the last figure, we see that the velocity actually is high. So our model behaves correctly in these ways. However, we expect to see some turbulence there, but since it is a static model, that limitation is provided by the program. So we cannot see that, although we put the properties of the plot in the program. Next, please. And we assess the shear stress. And the question is, why shear stress? The wall shear stress is defined as the tangential force per unit area that is exerted by the flowing fluid on the surface of the tooth. And it is highly related that nowadays shear stress is a maker to see if there is a formation of flake that is a phase of the atherosclerosis disease. We expect that in normal artery there is 10 to 70 grade of shear stress, and the units is 9/seconds meters. We found that in a paper if we transform that into pascals, we saw the relation that 1 pascal is 10 9 over centimeters square, and our shear stress is around 4.5 Pascal. One might see that this can be actually good. However, we see that the average peak systolic of the wall shear stress in the aortic is around 1.79 with an error of 0.71 pascals. So the maximum shear stress, according to also literature in the aortic, is around 2.4. So our model has a great difference of shear stress. And the reason why we believe that this is the shear stress is because our model is not completely open. However, the simulation is correct. Next, please. And with the pressure, when there is a systolic phase, we need to have a pressure enough to open the aortic valve that is around 80 millimeters of mercury. And what we did here is that the flow is entering from the red circle in our image, and the pressure that is in the right corresponds to the environmental pressure plus the systolic pressure that we put, and we put around 120 millimeters per mercury. And we see that in many simulations, they use this systolic pressure. And we assess to know what is the pressure before the valve, because it's very important to evaluate if we could develop a grade of stenosis in which the pressure of the chamber of the left ventricle will be more higher than the pressure that is after the valve. So here we see a difference of the systolic pressure after the valve and before the valve. That is around 6 millimeters of mercury. So it is in the normal ranges of pressure, because to assess, for example, for hypertension, which is a disease of high pressure, systolic more than 140 and diastolic more than 90 number, we see that we are in the correct range, so we could evaluate that this is correct. Next, please.
In conclusion, with this design, we simulated the flow throughout the aortic valve after the systolic phase, and we obtained the result that the wall shear stress in the aorta is 2 pascals more than expected. We managed to achieve our general objective, which was to perform the static simulation of a porcine aortic valve during the systolic phase, and also our specific objectives to simulate the pressure and shear stresses in the artificial aortic valve in a static model during the systolic phase. And also we evaluated a design previously implemented to determine the reliability of our model.
Well, for future work, we see that we also have to put the geometry of the ascending aorta, descending aorta, and the aortic arch, because we need to see how the flow behaves in those areas which are responsible to deliver the oxygen to the body. For example, for the aortic arch, we see that it's very important that we do not generate actually high shear stresses, although there is an area that has like kind of shear stress, because the flow is going, for example, to the brain. And for the descending aorta, we need to see that there is also a pattern correctly that delivers the oxygen to all the body. We also want to compare with other bioprosthetics valves models that are currently applied for the same purpose. For example, bovine aortic valve are actually developed nowadays, so we can assess a difference between the porcine and the bovine valves because they are bioprosthetics. And an obstacle that persists during the study is that we couldn't place a material of the valve. This is a limitation that the software actually gives to us, so we could not put, for example, the the tensile modulus, the tensile strength of the valve. So it will share us some results that might be not reliable, but since we compared the results of our shear stresses, our pressure, and our flow pattern, we could assess that actually our simulation is good. And we also know that since this is a static assessment, we need to have a dynamic point of view. So we need to use softwares like help us to achieve that, like for example Console, because we know that in every time there is the flow is actually a living thing, and the valves are contracting, are relaxing every time. So we need to assess that possibility as well, and that will be everything. Thank you.
And here are our references. So thank you very much for your attention. Please leave your questions in the comment section below, and we will answer as soon as we can today. Thank you very much.